as today's speaker. He completed his BSc from Presidency University. Presently, he is doing his integrated PhD from University of Massachusetts Lowell. Today, he is talking about how to make satellite chip edition. Requesting everyone, please mute your microphone and turn off your video. If you have any question, then please write it in the chat box or raise your hand. I will take those questions after finishing the talk. Thank you. Over to Shunipta.
Hello everyone. It's kind of early morning here, so my voice still hasn't woken up. So you may have to deal with that. So can please everyone let me know if they can hear me clearly? Am I audible? Am I speaking clearly?
Yes, Shunip, we can hear. By early morning, do you mean 9?
I didn't hear you.
By early morning, do you mean 9 a.m.?
Yes, it is very early for me.
Yes, that's okay. Yes, we can hear you.
Oh, great. Okay, so I'll turn off my video because who wants to look at my ugly mug when I'm speaking, right? But I'm here, and with that, I'll start. Let's go. So the title of my talk, let's dig into that for a moment. So I'm talking about how to make a satellite, and I want to do it for cheap. I want to focus on this cheap aspect a little bit first because, well, I'm a student, and I want to make things cheaply because otherwise no one would give me money to do that. That's why it's a cheap edition. And why I want to make a satellite? Because first, I kind of like it. I like to make things, and a satellite goes up in space, it does things. That's kind of appealing to me. So the first part of the title is personal, and the second part is more practical. With that, I'll start actually talking about how to make a satellite for kind of cheap. Okay, let's progress. So the largest barrier to entry for any satellite is really the launch price. The launch price is a huge chunk of the budget for any satellite project. The plot that you see on the screen, on the x-axis, it plots the mass of the payload, the cost to put the payload to 100 nautical miles, which is 185 kilometers altitude, which is rather low if you think about it, because the International Space Station is at 400 something kilometers. And the orbital inclination, meaning the maximum inclination, meaning the latitude that it crosses, is 28.5 degrees. So basically, as it goes around the Earth, it goes from minus 28.5 south to 28.5 north. And the price is given in dollars, really. So that's the kind of the total cost. And on the y-axis, we have cost per pound of payload, which is also in dollars. And you can see that the least amount that you put in the payload, the more costly it is. So the initial launch vehicles like the Pegasus or Minotaur or Taurus were very expensive in terms of cost per pound. Per pound is per half kilo. But as you go on to the heavier launch vehicles, like the Delta IV Heavy, the launch price is actually reasonable per pound. It's like 5,000 pounds, $5,000 per pound of payload. But the problem is the amount of payload that you need to put there to get that kind of a launch still makes your own personal launch prohibitively expensive. And that's where SpaceX with the Falcon came in, and they wanted to give $5,000 per pound for literally anything. You make anything, you're gonna pay $5,000 per pound. And they could do that because parallelly to the launch mechanisms maturing, the rockets maturing, some other developments happened on the side. And we'll talk about those developments in a minute. This is a projection of launch prices. So on the y-axis, we have $1 per kilogram of payload. And on the x-axis, we have flight rate per year. And the cost is actually broken down into different parts. And this projection was from 2016, actually. So we have progressed quite a bit along the way. Now, as you can see, any satellite launch needs facilities and development. Like you have to make a lab, you have to have a clean room assembly where you can assemble everything, test everything. But once more projects get going, the infrastructure is already built. You don't pay for building infrastructure twice. So as the number of launches increase and as more and more places have infrastructure to build satellites, that cost goes down. Instead, as we have more launches, the hardware cost goes up and the maintenance costs go up. But that's not as significant compared to facilities or development costs. So it's kind of important that we try to make as many satellites as we can. But to make many satellites, we need to have many technicians who are trained on this process of making a satellite, which doesn't sound too easy. At least people don't make it sound too easy. So that's kind of where the next thing that I'm going to talk about comes in. So CubeSats actually revolutionized the field of satellites and made it accessible to even students. What is a CubeSat, you may ask? A CubeSat is a small satellite. It's made of 10 centimeter by 10 centimeter by 10 centimeter standard units. And these units are called U, 1U. And these are typically 1 kilogram per U. And what people usually do is, because it's hard to fit anything in a 10 centimeter cube, they usually stack these on top of one another. So you stack 2 1Us on top of each other, it becomes a 2U. You stack 3 of these together, it becomes a 3U. You take 2 3Us and strap them together, it's a 6U. And you take 2 6Us together and strap them together, it's a 12U size. And these are common standardized sizes. Like if you go online and search for CubeSat standard, then you'll see that there is a standard document explaining the sizes and shapes of the CubeSats, like what you have to make it compliant with standard buses. The thing about normal satellites that people make for specialized things, for example, communication, providing TVs to our home, those things usually come in weird shapes. And that's also something that makes it hard to put a couple of these together in one launch. But since CubeSats have one standard size and they're small, they're cheaper to build. And you can put many of these actually together for ride sharing. So the cost per pound or the cost per payload actually becomes much cheaper. And the other good thing about CubeSats is since they're smaller and cheaper to build, you can put them up in space in a swarm, like many of those working together. And a good example of this would be the Dove satellite, which is actually pictured on the top right. It's basically an optical telescope that looks at the ground in 4 wide color ranges. And most of the agricultural data that people use nowadays is from Dove. Dove satellites are made by a company called Planet Labs. In fact, if you remember, India made the world record of most number of satellite launches, I think a couple of years ago, with 104 satellite launches, and 88 of them were these Dove satellites launched by Planet Labs. And currently, Dove gives total global coverage at any moment of time, meaning day or night, they have got you covered. They can take pictures of you. And Dove is actually impressive in its technology because on a 3U form factor, the entrance aperture is basically 10 centimeter diameter circle, right? That's the maximum it can be. And with that, it can have a resolution of about a meter, less than a meter. And that's very close to diffraction limit. So that optics in that satellite is something. I can tell you that. So with that, I'll give you some statistics of CubeSat launches. This only dates to 2018. But if you look at it, the CubeSat concept actually originated in 2002-ish. And in 2005, there was the first educational launch because the idea behind CubeSat was invented, the concept of it at least, was invented in as far as I remember, UC Santa Cruz. I could be wrong. Please correct me if I'm wrong. Um, but the main goal of that was education, to open satellite design and the experience of actually flying something in space more accessible to students. But then, as time went on, people started to think, okay, if this is a platform where you can make things small, and as technology progressed, everything gets miniaturized, why not develop the new technology that can be smaller and still work? So as time goes on, you'll see that there are more launches that cater more to technology development. And suddenly in 2014, you see a jump where a lot of remote sensing satellites come in. So from 2005 to 2012, that took out to 2013. That's how long it took to mature the technologies to apply the concept of CubeSats to remote sensing. And as I said, the idea of making smaller things which are cheaper, which can be launched for cheap, and in a swarm possibly, is really attractive to anyone in the remote sensing business, because you want to be able to give people as real-time data as possible. So in 2017, that's when Dove launched the Planet Labs satellite. You see that big spike of launches just because of remote sensing satellites. But you'll also see that the number of education satellites have really not gone down, and we have more science experiments and communication satellites on top of that as well. So yeah, I guess it's a great time to build your own satellites with very little money. And in India, I was looking at the ISRO website to prepare for this session. According to ISRO, we have had about 10 small satellite launches. They're small satellites because they list all like mini, nano, and pico satellites. Mini satellites are anything below 100 kilograms. Nano satellites are about 20 kilograms or less, and pico satellites are less than a kilo. These have been developed and flown by universities in collaboration or by themselves. The picture on the left is a satellite called Jugnu. Jugnu in Hindi means firefly, by IIT Kanpur. It's a payload that I'm going to talk about in a little bit. And the goals of these satellites have been technology demonstration to remote sensing, science, and education. Now, if I want to talk about designing a satellite, I need to kind of think about what are the parts of a satellite that makes a satellite. And you can take a satellite and basically chalk it up into two basic parts. One part is mission systems. So mission systems only cater to the mission itself, like a remote sensing satellite, for example. Its mission is to remote sense, and to remote sense, it needs something, some form of a payload that will do that. And that's it. Mission system does not care about anything else but the primary mission of the spacecraft and the launch. And to support that, you need other systems which are categorized into bus systems. This is basically the body of the spacecraft, the satellite with other stuff in it. And the other stuff would be attitude, determination, and control. Attitude in this case is not, oh, is this person angry or sad or what? Attitude is, it's orientation in space. Because at that point, you not only have the velocity, the position of the orbit, you also have like its pitch, roll, yaw, and linear angular momentums, all of that. Then you need communications to actually send the data collected by the payload to ground, because most satellites burn up on re-entry, and it's very hard to recover anything from them. You need a power supply to power everything, the bus and the payload itself. You need a system to accept commands, send commands to the payload, keep everything in check, and handle all the data, hand it to communications, for example. And to house all of this, you need a structure. So these are the basic parts that a satellite has. And if a team of students have to design a satellite, they have to kind of start with this diagram, that this is my mission, this is the payload that I need to design for it. And then you have to come up with, okay, if this is my size, then how do I do my attitude control? How do I do my communications? What I need for power supply, and so on and so forth. It's how you think, and then you fit it all in a given structure. For example, if you're designing a CubeSat, it would be a CubeSat compatible structure. This is a standard satellite. It's a Landsat 4. Landsat is one of the satellites that that provided plethora of remote sensing data for the ground. The Landsat is a multispectral imager, which images in, I think, over 20 bands, if I'm correct. So bands would be small wavelength ranges, all the way from near infrared to the end of visual spectrum, if I remember correctly. And if you look at this diagram, it has all of those parts. It has X-band antenna, direct access S-band, high gain antenna. Those are for communication systems. Then there is a command and data handling module. There is an ACS module. There is a propulsion system, which also is a part of the ACS module. There is a power module and all of that. So, and if I go on to the next slide, this is a diagram of the Jugnu satellite, and you see it kind of has the same parts. There is a structure, there is communications, there is power, thermal systems, and other parts of it. There is ADCS, attitude determination and control. So no matter how big or small your satellite is, the design procedure is the same. It's only the scale that would be different. With that, I will start talking about my own work now. When I joined in 2016, I started actually working in the lab kind of seriously in 2017 summer, because I spent the first 2 semesters taking courses like normal people. In actually close to the end of the summer, I was given the opportunity to design a small imaging system as a part of the Google Lunar X Prize project. This project has, like, the Google X Prize was actually withdrawn by Google because everyone was taking too much time, and they probably didn't have the million just sitting around. But I was tasked to design a small imager that would go on a lander on the moon. So that's when I came up with this Payload comic. It's a compact multi-channel imaging camera. So it's small, it's multi-channel, meaning it can do multispectral imaging, and it's a camera. It's like a normal camera, really. I'll show you that in a moment. This is how it looked like when I first made it. You see how janky this looks. It was literally 3D printed plastic because I don't know how to machine metals. I covered it in aluminum foil because, well, 3D printed plastic is transparent, and light getting into camera from other sides is not a good idea. That green PCB is just the camera control board, just hot glued to the top of it. That's it. That's how it looked. But then, with a little bit of time, I think 7 months, some more experience, and $1,500 down the drain, that became this. This is a CubeSat compatible housing for comic. So, and it also integrates everything, including a computer that can operate the camera, get the data, and push that data out through Ethernet connection. You can see that on the picture on the right. There is a little 9-pin connector that provides power, 28 volts, which is a standard power voltage, because 28 volts is the voltage of most of the battery packs that are used in space applications, and an Ethernet port.
Sunip, I'm sorry to interrupt.
Yes, please.
Can I just all the slides, or most of the slides, when we are seeing it, it
Yes.
seems very low resolution. I mean, are the sizes really small or something like that?
No.
Or okay.
It looks great on my end. I'm not really sure.
Okay, so for example, in the current slide,
You can make out the labels in the picture?
The picture on the left, I cannot read the labels. On the right, it's slightly better.
Okay, that's weird. That's unexpected. It could have to do with my upload speeds or something, because I know that they're working on the internet right now.
Okay, okay, then just go on, please.
Okay, yeah. If you can't read anything, just let me know. I'm here. I can read it out for you.
Okay.
But since Dr. Chatterjee pointed that out, I'll kind of read out what's on the picture. So the satellite, the payload, I mean, on the left, the bottom part of it is the optics housing. It just houses all the optics, like the lenses, the film, and the CCD, all of that. And on the top, we have the electronics housing, which houses a little Raspberry Pi, which is like a 600 rupees thing, and a power breakout board that I designed to take the 28 volt and make it 5 volts and 12 volts for the camera and the computer and so on. And on the right, in the picture on the right, you see that there are kind of two rods that extend all the way to the end. Those are Cubesat Rails. So Cubesats kind of go on a rail so that it's kind of easier to push them out into space from their launchers. They're quite literally like, if anyone here plays computer games, like the grenade launchers in there. You just plop them in and shoot them out. It's really simple and elegant solution. This is the optical design of the payload itself. I'm going to talk about it a little because it's optics, and full disclosure here, I hated optics when I was an undergrad student. I didn't know what I was signing up for in my PhD, and I was actually quite sad that I would have to do optical designs. But when I started actually doing it, I really loved it. So this design, for example, it's kind of cool because it has three parts that does three different things. At the front, I have two lenses. What that does is it takes light coming from infinity. So they're like parallel beams of light, right? And they can come at any angle depending on where the object actually is in the sky or where you're looking at. But the goal of the first part of the optics is to take all of those beam cones coming at any angle whatsoever and make them focus on a focal plane such that all of those beam cones focus parallelly. And this is required because to have multispectral ability in such a small form factor, I could not have employed a system where I take the beam and I converge it really slowly so that they are kind of parallel at the focal plane. I couldn't do that. So, and interference filters that you typically use to filter out light, they need this kind of very normal incidence. So this is called a telecentric design. It's a telecentric image plane design. And the first two lenses does that. It makes the focal plane telecentric, and that's where I place my filters to filter out the light. But the other problem with this is this focal plane is really large, and you cannot buy smaller, cheaper detectors like CCDs that are this big. So now to make it fit on a smaller detector, I have to have all of the rest of the optics. Two lenses to make the beam collimated again, and one final lens to focus it down onto the detector plane. The entire design is like 260 millimeters long, but a CubeSat is only 100 millimeter by 100 millimeter on the side. So I had to add 2 fold mirrors to get it all fit in a 10 by 10 centimeter squared kind of area. And these are the actual optical components in the housing, sitting in the housing before full assembly. Now, what does it do? Like, what are the kind of characteristics of the final assembled camera? So it has a large field of view, 35 degrees by 25 degrees, which doesn't sound large in terms of a phone, but it's kind of large for a small system like this. And that kind of translates to 315 by 225 kilometers squared from a 500 kilometer altitude in orbit. And the resolution of the instrument is also quite high, meaning the angular resolution is 0.1 degrees, which is not going to impress any astronomer who is listening to this talk, which is about 800 meters at 500 kilometers. The sensitivity is where it kind of shines. It has a sensitivity of 0.1 counts per pixel per rally per second. That's a mouthful. So that essentially means that if I have one rally coming at per second coming at a pixel, then I'll register 0.1 counts. So in like 10 seconds, I'll have 1 count. A rally is a unit used by mostly used by astronomers and aeronomers alike. It basically is 10 to the 10 photons per meter squared uh, from basically just coming straight down, as far as I remember. Anyone can point me out if I'm wrong about that. And the design also supports a wide operating range. Like it can take light from 450 to 900 nanometers. After 900, the optics can work, but it kind of hits the thermal limit, and the detector sensitivity also goes down. The comic also supports very narrowband filtering, just about 1 nanometer full width at half max, because of that telecentric design I was talking about. And in that filter, you can just break it up into parts where it then becomes a mosaic. It's not one filter anymore. It's a combination of filters. And you can put up to 15 of these different filters together in that mosaic. And you can do push broom imaging, which I'll explain in the next slide, to get multispectral images of a complete scene. Commercial components only, and to build the whole thing, I think it cost $6,000, and the most expensive parts were the filters that I bought. I think they were $4,000. It is, again, I said, it's less than 1U. It weighs 1.25 kilograms. Actually, 1U allows 1.33 kilograms, and it uses only 4 to 6 watts. And this is what the concept of push broom imaging looks like. You basically just take a broom and push it. So you basically cover all the ground. On the right is basically the filter mosaic that I'm using right now. It has 4 filters from the left to right. It's 500 nanometers, 589, which is sodium, 770, which is in the infrared, and 700. And the colors kind of look off because 500 should be green and 589 should be yellow, but that's really just the light balancing, the white balancing of the phone camera, because it's very monochromatic kind of light, and the white balancing just doesn't do it justice. Now, if you imagine that filter assembly, if I just move it from the left to right, any point on the wall will actually cross through all the 4 colors. That's basically the concept of push broom imaging. Now, what is it good for? I can give you a very crude example. Like this is from when I was first building it in that weird 3D printed case. And even the fold mirror had some corrosion on it. That's why on the left you see some dark hazes. But what's interesting on this picture is, I don't know if it's bright enough or you can see it properly, but the part that I've highlighted in the white oval is a tree. That tree is actually, part of it is being imaged in 770 nanometers and part of it is being imaged in 700. And the chlorophyll, the thing that does the photosynthesis, is really absorbing in 700 nanometers. It's the red part of the spectrum, and that's where it takes a lot of the energy from. But in 770, in infrared, it's reflecting everything back. That's why in the 770 panel, the tree looks white, because it's just reflecting all of the infrared light that is getting out everywhere. But on the 700 panel, it's dark because it's just absorbing almost everything that it gets. Now I can talk about milestones of this. On the left, you can see the balloon mission that we did. It's actually near space qualified. It has been up to 40 kilometers of altitude. You can see that it's flying and the ground is receding. This flight has had a few problems, even though it lasted 22 hours. So since I can't control this from the ground once it launches, there's a software routine on the camera that basically looks at all the images it takes and adjusts the exposure. Right now it's doing just a 1-point system, meaning it's taking all the pixels and making sure that most of them are below a certain threshold, but that's actually not good enough as you go up in space, because some wavelengths are really bright, especially in the daytime. You can see that it's blasting in yellow and green and also kind of the red. It's only the infrared where things are kind of better. So there's another flight we are planning in March 2021 on a high altitude balloon with a new filter mosaic that's going to do aeronomy, meaning it's going to look at emissions from the ionosphere and the upper atmosphere in general from things like oxygen, nitrogen, that are excited by the ionospheric radiation and solar radiation, like solar UV and photoelectrons and all of that. It has been recently absolutely calibrated with standard sources so that I can do photometry when it comes back. In fact, this is going to be part of my PhD thesis. And a lunar exosphere imaging proposal is also in works with the same payload. And now, since I'm kind of working from home, I actually wanted to do this presentation from the lab where I could like show you guys things from the lab, but I can't. So instead, I have set up this camera next to me on a table, and I can show you how that looks right now. So that's me on my camera. The image is a false color because the CCD is really monochrome. I'm doing some processing at my end to give the impression of colors, but yeah, you can see me in there. And that little artifact that you just saw is just coming from the software. It has nothing to do with the actual data that's being taken. So as you can see, it tells you like the exposure right now is half a second because this room is pretty dim. And this instrument, all it cares about is keeping the exposure time under 120 seconds and expose things as best as it can, not like a cell phone camera or any normal webcam whose priority is to show a person. With that, I'll move on to the next part of my talk, which is Spacehawk. So the first thing that I talked about is a payload. It is not on a satellite yet. But Spacehawk is actually a satellite that UMass Lowell students are building. Spacehawk is an acronym, and it actually stands for this whole thing: Science Program Around Communication Engineering with High Achieving Undergraduate Cadres. This is a NASA-funded project. It's funded under the NASA USIP program, which is catered to undergraduate students so that they can make their own satellites. The goal for Spacehawk is actually quite impressive. We want to show a phased array communication with high data rate, which I'll talk about in a bit. So on the left, you see the spacecraft bus. Like that's the actual mechanical structure where everything will be housed in. We haven't assembled it yet, but because all the payload actually is being tested right now. And these kind of satellites are kind of hard to put together. And once you put them together, they're kind of a pain to take apart. So we'll just do it at the end. On the right, you can see a mock-up of the satellite itself. The things on the sides are the solar panels, and the circular hole at the front is basically a webcam. That's what we're going to use as our data source. This is kind of an exploded view of the satellite, and like the other pictures that I showed before, it kind of has the same parts. It has some transceivers and antennas for communication. It has a bus. It has a mechanical bus. It has an ADCS subsystem. It has a power system. It has a camera. So all satellites are kind of standard. They're built in the same way. That's the kind of the point I'm trying to drive home. Here's a bit more description about Spacehawk. It's a 3U CubeSat, 34 by 10 by 10 centimeter cube. The 34 is actually with the rails, which extend a bit at the two ends. And it's about 3 kilograms. And the goals of this project is to provide undergrad students with the experience and opportunity. And the technological aspect of the goal is we want to demonstrate a high data rate system in the X band. X band is about 7 to 8 gigahertz, where we want to do communication with beam steering, but not by moving a dish in space, but by using a phased array antenna. So in this case, we have 16 small antennas that all go together. And by changing the phases of the output on those 16 antennas, we can do constructive and destructive interference to actually steer the beam around. So this will go on a resupply mission, I think SpaceX 23, onto the ISS, and then it'll be launched from the ISS into space. And it'll basically share the orbit with ISS at 400 kilometers and 51.6 degree inclination, meaning it'll go from 51.6 south to 51.6 north as it does a complete revolution around Earth. The operation goals of Spacehawk are as follows. So we want the spacecraft pointing to the sun because we want to have as much power generated as possible. This X-band radio is very power hungry. It takes about 30 watts to operate. And since initially when the satellite is launched from the ISS, we don't know anything about its orientation. Even like this satellite itself doesn't know which way it's oriented. So the time it takes to take it and point it to the sun is kind of critical because it only has a certain amount of charge stored in the batteries. And if you run out of that charge before you start charging, this mission is doomed. So we want this to be able to point before the spacecraft goes energy negative. We want to have it pointed stably so that the primary payload, which is the X-band communication system, can send data down reliably without having to change its phases too much. And if anything weird happens, let's say we are hit by a micrometeor, which the satellite actually survives, then it's going to be whacked out of its attitude, like the stable attitude. So it has to be able to recover itself in a smaller time scale than the lifetime of the satellite. These are kind of parts of the requirement. And for the X-band system, we want it to be able to search for a ground beacon signal, then lock onto it, and then transmit the data. Like it has no knowledge whatsoever where it is in space, where the ground station, meaning we are, and it just has to do everything blindly. Now, these 4 points that I just highlighted, they actually all pertain to the attitude determination and control system of the bus, because again, like I said, the payload is only concerned with getting the beacon signal, locking onto it, and transmitting data. It doesn't care about anything else. But it's on the ADCS system to provide it with the opportunity to do that. For the rest of the talk, I'm going to talk about the ADCS system itself because it has a lot of physics in it in this project. Like I have worked on different parts of this project, but this is the only part where there is a lot of physics, and I can actually talk about this comfortably with all of you because we all come from a physics background. I'll state the requirements that we have in like more concrete terms now for the attitude control system itself. So the spacecraft has a 6-month of nominal lifetime. We want a final angular speed of 10 RPM about the z-axis of the spacecraft. I'll define the axis really soon. Why do we want to have an angular speed? Because as we all know, if you spin a wheel, it rolls along the ground for some time before toppling. Angular momentum is kind of hard to change. But as it rotates about its z-axis, the angular speed will have some nutation about the z-axis. And we allow the nutation to be less than 5 degrees because, sine of 4 degrees is 4 degrees in radians. That's a good number. It's a small angle, so everything is good. The sun pointing accuracy also needs to be less than 4 degrees because that really maximizes the power throughput. This other point is really not concerning the ADCS system. It's more concerning the power system, but it's kind of important that we have to be able to charge from the albedo of the Earth, meaning whatever the Earth reflects back in the worst case scenario to stay power positive. And the spacecraft has to achieve all of this against disturbance torques. Disturbance torques are basically what pushes you out of your alignment. And at that kind of altitude, the biggest contributor to disturbance torque is actually aerodynamic drag. Like you can think that 400 kilometers is a lot, but there is still enough atmosphere in there that produces significant amount of drag. In fact, if you look at the ISS does these boost maneuvers where it pulls up its orbit because the drag really pulls it down all the time. The other problem is gravity gradient, because at that altitude, and since this is a kind of inhomogeneous spacecraft, the center of gravity and the center of mass actually don't match up. So the Earth actually just tries to pull the center of gravity to itself. So you can imagine that it will basically rotate about the center of mass, and there will be a torque at the point of the center of gravity because of gravity. So these are the disturbance torques that we have to work against, and we also have a limited power budget of 30 watt hours. And also we have to do it for cheap because the money that we got for this project was $500,000. That sounds a lot, but $250,000 of that is just for the launch, and we have the rest $250,000 to do the project, and that has to pay the students working on the project. From that, we have to buy all the components, and so on and so forth. So it was kind of important that we did everything for cheap. Now, how to do propulsion in a small sat? The typical ways of propulsion are using propellant thrusters. So you just push some gas in it and you burn it. You can use ion thrusters. So you just push out ions using electricity because that's kind of easier. You don't have to deal with explosives. You can use something like a solar sail, but that has the problem that it's huge. Momentum wheels can be used, but they're kind of large, they're kind of big, and controlling them can be hard because you have to then bleed out the momentum that they gain over time. Then there are magnetic torque coils. These are like small coils that generate a magnetic moment that push against the Earth's magnetic field itself. And if you can design your satellite cleverly, you can use gravity gradient also to stabilize your satellite. I was saying ion thrusters and propellant thrusters can be expensive. Here's an example of that. The picture that you see on the left is an ion thruster. It's actually using liquid metal. That's like an alloy of gallium and some other things to produce the ions that give you the momentum. That little thing, it takes 1 U of space, so it's kind of big, and it costs $45,000. And that's more than a lot of people get paid in the US over the year, just for perspective. So we couldn't go that route. So these are the components that we choose. These are the measly components. So we are using a magnetometer for angular speed measurement. Some of you may ask why we're not using a gyroscope. In fact, the little board that we're using, I think it's like $5, $10. It actually, that little chip is also of similar price. It actually has a gyroscope, but we are not using it because we can't test it. You need an air bearing, which basically is 3 bearings that can rotate the spacecraft around to kind of simulate the gyroscopic effect. And there are no available ones for such a small spacecraft, a 3U spacecraft. So we ditched the gyroscope the moment we decided on this chip. So we're going to use magnetometer for angular speed measurement, and how we do it, I'll talk about it in a bit. There are Lux Sensors, which basically just detect light, and these are for coarse sun pointing. They basically just will tell us if the sun is like up, down, left, right, in the front, to the back, that kind of thing. We have one expensive sensor for this system. It's a 60-degree field of view sensor that will do fine sun pointing for us. It's basically a quad cell photodiode. So basically by looking at the difference of brightness on the 4 cells, you can tell where the sun is. And it has a half-degree accuracy. And we are using magnetic torque coils to control the spacecraft orientation because it's a cheap solution. It doesn't require a lot of power, even though it actually takes some time to work, because the kind of torques that this thing produces is of the order of micronewton meters. We have one computer for the ACS, the attitude control system, and the payload. And for future projects, I'll actually just have a microcontroller on a separate board to do this. But that's irrelevant for our discussion. Now let's talk about the algorithms that we actually use to determine omega and apply our torques and stuff. This is where a lot of the physics will come in. And let's get familiar with a couple terminologies here. So the first term is tumbling. So tumbling is the random motion, or in this case, the rotation of the satellite after launch. And there's no way of knowing what this will be. And detumbling is the process of spin stabilizing the spacecraft, meaning you come out of this random rotation and you align the omega, the angular velocity vector, with the body frame z-axis of the spacecraft. And now we can define the body frame's z-axis. So the long axis is z-axis, and We'll basically take x-axis to be parallel to one of the faces and use the right-hand rule to find where the y-axis is. And we will also orient the magnetic torque coils in x, y, and z directions. Then we have to spin up because we have to reach our target angular speed of 10 RPM, which is about 1 radian per second. Now, to do that, we need to first measure the spin rate, right? To measure the spin rate, what we do is we measure the magnetic field at discrete time steps. And then we basically just do a forward derivative to calculate B dot. And omega is given by B dot T, like B dot now cross B dot last time over delta T and norm of B dot squared. From the perspective of units, this kind of makes sense because omega has unit of 1 over time. And at the top, you have B dot cross B dot, so that's B dot squared. And at the bottom, you also have B dot squared. But that may not be enough. So I have a little infograph to kind of show how this works out. So let's say this is B that's measured at time T now. And then I measure B at the next time step. So the previous measurement is still there. Now I know the direction of B dot T. So if you are using just a forward difference, it's just the direction of B now and B previous time, right? And let's take the third measurement now and take the second derivative. So now we have 5 vectors that we have to work with. Now, if I group all of them together, because I can translate vectors, on the left, you can see B changes kind of clockwise. And if you do the cross product, you'll see that omega, the direction of omega is counterclockwise. This makes sense because omega is in the body frame of the spacecraft. And as it looks at B in its body frame, it'll see B going clockwise if the spacecraft itself is going counterclockwise because B isn't changing direction that much over that course of time. I hope that that explanation kind of is practical enough for you to agree with me that omega can be estimated in this method. Now, this has some obvious problems. One of them being if B changes really slowly, then B dot can be really small, and the way computer does math, we can have an overflow. And if omega and B are aligned, then B is simply not changing. So you can't just evaluate omega anymore. That's another problem. For both problems, what we do is we put a filter on the data and we actually keep a long track of B dot, and omega so that we can kind of, we can filter out any jitter coming from these kind of behaviors, small denominator and such. And also if omega and B becomes aligned at one point, this diagram will really help. Like I said, the satellite is on a 51.6 degree inclination orbit. So it'll go from the northern hemisphere to the southern hemisphere. And as you look at this diagram, the field lines actually change direction in the 2 hemispheres. So even if things get aligned for some time, since the orbital time period is 90 minutes, it's going to come out of alignment really, really soon. So that takes, like, nature takes care of a lot of my problems. So with that, I can now say how to actually achieve this process of detumbling. So these torquing coils, they can only turn on and off. So I have to torque them in a way where this thing can be achieved by, like, this whole process of detumbling and spin up can be achieved by just doing this, just turning some torquers on and off. We just have to know how and when to turn it on and off. So this is what gives us the direction of the dipole. So LT, L subscript T, is the target angular momentum, and L is the current angular momentum as measured by the spacecraft. So the spacecraft will be given its moment of inertia matrix after it has been assembled and it has been measured. And by measuring omega, it's a simple matter of doing I omega to find out the angular momentum. Then if you do B hat cross the direction of the change in angular momentum that you need, that basically gives us the dipole direction. How, you may ask? I can work out the math. So If mu hat is in that direction, then torque is mu cross b, where b is the Earth's field. And if I work out the math, it has two terms. The first term is in the direction of the change that I want to do. So that's the part of the torque that's going to pull L to the direction to LT. And the second term is actually in the direction of minus b hat. So that's the term that's going to rotate the space, like align the spacecraft in a way which is opposite to the magnetic field, which is just the case of the magnet. If you have a magnet, then the south pole of the magnet will, like if you have two magnets, the south pole is attracted to the north pole, right? So it's just that. The second term is the spacecraft behaving as a magnet, and the first term is what we can use to make the detumbling and spin up both algorithms actually work. And for the alignment that wants to happen, nature is going to take care of it, as B itself will change direction over time. And again, as the satellite has a given spin, it'll be much harder for the magnetic torque to kind of rotate the spacecraft around. The next step for the ACS algorithm is sun pointing. Once we have detumbled and spin stabilized, we have to take the satellite, which is now in any random orientation, but in a spun up state, but we have to now point it to the sun. We use only one torquer, the Z direction torquer, to do this. And it requires the knowledge of the sun vector, which is determined by using the coarse sun sensors or the fine sun sensor, depending on which one can see it. The amount of torque is actually given by this. So it's not really the amount of torque, but because these things can only produce a maximum amount of torque, right? You can just put any amount in there. So this will just give you like the kind of the percentage of torque that you should apply at any given moment of time. And since this process is iterative, if you overshoot or undershoot, you can correct it at the next step. So this really awkward expression is what's going to give us the amount of torque that we need to produce. I'm not going to delve really deep into this because there are too many terms for me to work out in this talk, but since we're all physicists, we can sit and work it out, and you'll see that this will try to align the S vector with the S vector at the end of all the operations. Now we have to implement this algorithm in a software, right? And to do that, this basically runs in a 10 Hertz loop. 10 Hertz means each iteration has 100 milliseconds to do its thing. And this 100 millisecond or 10 Hertz loop allows us to measure spin rate up to 30 RPM. If you take into account it's a 10 Hertz loop, then 5 Hertz would be Nyquist sampling for the spin rate that you can measure. And then give it another 1/4 that gives you 1.5 Hertz, which is about 30 RPM. Out of this, 20 milliseconds is spent in measuring the 11 sensors. There's one magnetometer, 9 coarse sun sensors, and 1 fine sun sensor. That's 11 sensors. And then the rest of the 80 milliseconds is spent in actuation. Like that's when the magnetic torquers actually run. They can't overlap because the magnetic torquers themselves produce a magnetic field, and you don't want to contaminate your magnetic field readings of like reading the magnetic field of the Earth with the magnetic torque coil readings. Any residual torque that actually builds up can be taken care of because it does a derivative, and the hysteresis is not significant in this kind of the kind of torque coil that we're using. And even if a residual magnetic field eventually builds up, it'll build up slowly enough that when we do V dot over a very small time scale, which is 100 millisecond actually, that's the delta T in the expression. The change will be small enough that any build up will totally be ignored by the math. So yeah, that's about it. That's kind of how it works. And for sun pointing mode, since I said the torquers can only turn on and off, we just turn them on and off with pulse width modulation, meaning in one time period, let's say 20 milliseconds. Let's say I have to keep it on 75% of the time. So it's on for 15 milliseconds and then it's off for the rest 5 milliseconds. And that's how we kind of tweak the amount of torque that's being generated. So any software of this kind needs to go through a few states. These are the states that the ACS goes through for Spacehawk. So at first it goes into detumbling mode, and then it traverses from there to night mode when there's no sun. And if it's detumbled and there is sun, but it's not sun pointed yet, then it goes into sun pointing mode. And when all of that is done, it goes into a ready mode where it gives command over to the payload to do its communication. This thing is written in NCC 99 because I am a standards freak. It's a nice program. I'll actually release it in GPLv3 at some point. Then you can actually take a look at it. But now that the ACS system has been developed, someone needs to test it, because no one is going to let me fly a satellite without testing it, right? So here comes the next troublesome part of developing a satellite. You have to test every system, meaning you have to design more systems to just test it. This is what verifies the ACS system. I know this picture is probably not clear. This picture doesn't say much or mean much anyway. It's a simulator that's written in MATLAB. This basically simulates the spacecraft's environment, meaning where it is in orbit, which the spacecraft doesn't know, but the simulator itself has to know because it's generating the environment. So it generates the magnetic field, it takes in torque measurements, and then it applies that and sees if the algorithm is working as it's supposed to work. And there's a front end that I have that kind of shows how this thing works, which I'll try to show you live at the moment. I'm actually running a simulation here. So this is a simulation that's running. This data that you see is coming from the mock satellite itself. So as you can see, the mock satellite measures magnetic field, B in milligauss. That's at the top, and it's updating in real time. And if you look at it, B is changing sinusoidally because the satellite is spinning. And that's what a spinning vector looks like when you decompose it in 3 components. It's a sinusoid. B dot is also a similar sinusoid. And as you can see, omega is right now being measured by the satellite. Omega z is at about 0.1 radian per second. And the angle between omega and z-axis is about 8.6 degrees. So that's actually going to go down to the less than 4 degree number. On the fourth plot from the top, there are 2 lines. The red line is the angle between omega and z, which should be 0, rather close to 0, which it is, which is the theta angle in spherical coordinates, r theta phi. And the phi angle, as the angular momentum vector rotates about the z-axis, the phi angle is actually just going from minus 180 degrees to 180 degrees and back. That's why it kind of has that rather slow sawtooth behavior right now, but as time goes on, as it spins up, that sawtooth will actually become more condensed. And right now, since it's kind of moving fairly slow, there's a lot of uncertainty in the phi measurement, but those uncertainties will also go away as time progresses. Just wanted to show you that. I could even like show you how it is running. So to run this part, like this simulation is running all in software. I just have one computer that's running MATLAB and a Raspberry Pi connected over serial cable. So over serial, it's accepting all the data for magnetic field and the sun vector, meaning the Lux values the algorithm should see. And then it's running its algorithm and doing its processing. That's kind of how it works. With that, I'll go to the next slide. So this is the hardware that I use to actually generate the magnetic field. It's janky. It's all on a breadboard and stuff, but it works. Uh, the reason kind of I want to show these images like this and not in a very professional environment, because I want you guys to know that anyone can build a satellite and a system to test it. All of these components that you can see on the table are those Helmholtz coils. Those are just borrowed from the physics department labs, like the coils that students use to do their lab, like normal class lab experiments on. These are just normal breadboards. They're just, all the circuit components are things you can find on any major retailer for rather cheap. And what's impressive is the simulator is running at 200 hertz, meaning the system that you see on the table on the left is changing magnetic field that is being generated at that rate, 200 hertz, with very cheap equipment. And as you know, a magnetic coil is nothing but just a wire, right? So as you send current through it, at first it needs a load of current, but as the back EMF generates, it'll like the voltage will change. It'll change from a short to actually an inductor, right? So you need a circuit that can supply current at a constant rate no matter what the back EMF is. So that's the picture in the middle. It's something called the Howland current pump, which is being driven by a couple digital to analog converters, which are taking commands from the simulation itself in Simulink to generate the magnetic field that I want. And I can show you in a later slide that it's a sinusoidal magnetic field that's generated by the system. On the extreme right picture, there are 9 boxes. You can see like 9 blue 3D printed plastic boxes. Those boxes house this core sun sensors and 9 LEDs. So by varying the brightness of those LEDs, I can simulate where the sun is. So this is just kind of me trying to give you an idea of how these things can work and can be developed. I know this is and it's kind of hard to fit all of this material in kind of a 35, 40 minute talk. I can talk about the simulation results a bit here. I have seen that it detumbles, meaning the spin axis aligns starting from a random orientation in about 1.5 hours. In fact, the result that you just saw, I started that at about 8:30 in the morning for me, meaning about 6 p.m. for you guys. So, and now the time is 10 here. So yeah, it has tumbled in about that time. Spinning up takes about 2.5 hours, and coarse sun pointing is the thing that takes the most amount of time because you can't torque all the time. So that takes about 1.5 days in the worst case scenario, and I'm trying to make the algorithm better to do it faster. These are some more plots from my visualization thing, but we can talk about that later. This is kind of a description of how the thing goes with time. So the black line is the angle between angular speed and the body frame z-axis. You see that it started off at over 100 degrees, but under 4 hours it came down to very close to 0 degrees. And then as sun pointing started, that angle also kind of deviated because it's applying torque in a different direction, right? And at the end of the day, it kind of stabilized at about 5 degrees in 12 hours or so. This is one of the simulations which started at a pretty bad initial condition. This is another simulation for which this ran for about a week, but I don't have all the data because I couldn't save it. MATLAB has some limitations on file sizes. But also here you see that it also detumbled in very little time. And sun pointing started, but we can see where it went because I don't have the data for it. This is just a plot from the simulator side, kind of showing where the satellite is at the point of time and the different vectors in a 3D space. It's not super relevant, but it's just there. With that, I'll stop. I'll take questions. I hope you'll have many. Thank you for giving me the opportunity to speak here.
Thank you for the wonderful talk. So I don't see any question from anyone in the
Wow.
chat box.
So everyone knows how to make a satellite now. Great. Please make your own satellite.
Sushantika, I have a question.
Okay,
If,
okay, go ahead.
if there aren't others, then
No.
SS
Please.
has also raised his hand. So Sunip,
Huh.
my question is as follows. You know, it was
Yeah.
very cute and exciting to see that you can really work on a tabletop and actually make a satellite, and you know, and this is really fascinating. It's so low cost, and you know, it's just a bunch of students getting together and building a satellite. My question is that the kind of satellite that you guys are making in the lab,
Yes.
what is your science goal? Like, for example, when you flew I understand that the building of the satellite part is one thing, but then
Mhm.
since it is related to your PhD thesis, I would be curious to know that what science questions would you be answering with the satellite and as well as with building the satellite?
Okay, I have to clarify. So this talk had two parts, right? The first part where I talked about my payload. The payload is part of my PhD. The satellite
Yes.
that I talked about has nothing to do with my PhD. I'm really a consultant for that project. It's just
Right.
something I did on the side. It's a side
So
hustle.
yes, so with the payload, what kind of science you are going to do?
So for the payload, the science that I want to do is I want to put this up in space, in near space, right? And I want to look at the upper atmosphere. So like I said, in the upper atmosphere, we have neutral oxygen and nitrogen atoms at that point. And as they're irradiated by solar UV and the photoelectrons that are generated by other processes, and also things from the ionosphere, as they interact, like this upper level of the atmosphere, it generates something called air glow. Because as these neutrals split and then recombine, it generates a faint glow. For example, if you look at pictures taken from the space station, you'll see that there are these colored bands. There's an yellow band. There's a kind of greenish band that you can see above the horizon. So my goal with the payload is to look at these air glows, and I'll also have a couple other instruments looking at air glow from the ground. Those are spectrographs. What I want to do is, I want to be able to predict the ionospheric weather by probing with these optical instruments. The problem of ionospheric sounding right now is that if you sound from the bottom up, then there are different depths you can probe, but you can go all the way to the top. And if you probe using GPS, like as GPS signal comes down, the ionosphere actually changes the GPS signal. And with that change, you can measure something called the total electron content around the line of sight for the GPS signal. But all of these actually just probe from either the bottom or the top. And you can kind of combine them, but you don't get much information about the middle. What I'm trying to do is I'm trying to use these kind of optical techniques to better understand the interaction between the ionosphere and the upper atmosphere where the air glow is produced. And if I find the correlation between the two, I can predict ionospheric disturbances and storms, which are actually of tremendous economical interest, because ionospheric storms affect power grids, communication, especially for the military. You know, the military has a lot of money to just spend around. So that's really the kind of people that payload is targeted at. But
Okay.
the satellite itself,
Yes.
it's totally for students. They're
Okay, very
building
good.
it. Yeah.
So I think SS has a question.
Yes, yes.
Well, Sunip, I have two questions. One is just about some technical thing about your payload, this filter. So is it
Mhm.
movable filter or
No, it's a mosaic.
so it's a mosaic? So how do you image the same portion of the field of view with different filters? Does
Okay,
the
so
satellite payload moves or what?
the payload moves. So if the payload is on a satellite, the satellite is in its orbit and it's moving, right? So the way we would orient the payload so that it would, like, the filter would be the perpendicular to the motion of the satellite, so that way we scan as we move along. For the balloon experiment, the
So
balloon yes.
sorry, so your scan rate has to be fixed with the velocity of the satellite.
Yes, but in most cases the scan rate is much larger than the rate at which the things like, for example, if I want to do agricultural study, a rice field will change in scale of weeks, for example. And then if I want to look at aeronautical things, those things usually change in the scale of a couple minutes. In a couple minutes, a satellite travels quite a lot. So, and also, like I said, with Spacehawk, I can spin stabilize. So what I can do is I can spin it really slowly and not rely on just the translational motion of it at all. I can just spin it and that way take the measurement and do something like an MRI really. I spin it and then I generate an image by deconvolving the spin and taking out the spin.
And the next question is about the small satellite making.
Yeah.
So you can build low-cost satellite, that's fine, and everyone can build them. But why should we put it? Why do you want to put it there just for fun?
No, not just for fun. For example, for me, since I already have Comet, if I get a couple $1,000 from my, I now have already built one. So I already have some of the infrastructure, like I was saying. Infrastructure building is a big part of the cost, right? Since I already have the infrastructure.
But so you
I can just
not only the satellite building, you must have some certain science goal.
Yes,
for the payload. So that cannot be achieved by some students. They have to be mature enough to make a payload as well.
That is definitely true, and that's where the PI of the project would come in. Like, no one is actually just funding the students, right? They are funding my advisor. He is now employing students that he thinks are fit for the project to do it. Of course, like, you need someone at the helm who is more knowledgeable. If you just let students do it, it'll be just for fun. Like, hey, can I light just a very bright LED that I can see from the ground and stuff like that. Yeah, that's the educational aspect of it. But like I said, the idea of CubeSats is manifold. Like, you can use it for many different things since it's cheap. You can just give people the experience that they can use later down the road to do these kind of things in the future at a larger scale. Because these things actually scale pretty well. The ACS algorithm, for example, that I developed, there's actually what's the name of this one? It's kind of a mini fridge size satellite that the proposal just got funded. That's being worked on right now, and I'm going to put the same algorithm that I put here, just with bigger torque coils and better magnetometers and stuff like that in there. So these things scale really well, and that is actually for ionospheric sounding with a radio. So yeah, so the science is there, but someone also has to know how to make the bus. You're absolutely right that students don't know how to do the science, but we need everyone, right? A satellite isn't just built by scientists; it's also built by engineers, and we need to prepare students for that kind of thing as well. That's kind of the idea for it.
Okay, right. Thank you.
Yeah.
So any more questions? Is there any question? Is there anybody who typed a question?
I don't see any question.
Yeah, me neither. So if not, let's thank the speaker for this session. And now we will move to the second second session of the talk, which is the interaction